Hi everyone, I'm Marco Gaido, and this is our survey on speech translation with speech foundation models and large language models. What is there and what is missing? Speech translation has been traditionally addressed as a task using cascade architectures. In this scenario, the audio is transcribed with an automatic speech recognition model. The generated transcripts are then translated with a machine translation tool. Direct architectures have become also popular. In this case, the audio is directly translated by a speech translation model. However, we have witnessed the emergence of a new approach, which is speech foundation model plus large language model, or SFM plus LLM. In this case, the audio is processed by an SFM encoder that generates a semantic representation of the audio, which is then used by a large language model to produce the final translation. As this is an emerging approach, there have been several attempts to perform it. So in this survey, we will check what is there and what is missing. First of all, we have created a high-level architectural overview in which we identified building blocks that are common to all SFM plus LLM solutions. First of all of them have a speech foundation model encoder, which extracts rich semantic information from the audio signal. And this is usually done with the whisper encoder or WAV2VEC. This rich semantic representation is then processed with an adapter, and this adapter is first made of a length adapter that reduces the number of the embeddings representing the audio sequence along the time axis, so it compresses the representation produced by the SFM, and common approaches are the CTC compression or using convolution with stride 2 to perform a 2D, a 2 times downsampling. And then the output of this length adapter is fed to a modality adapter that is responsible of taking the audio embeddings and projecting them into an embedding space that is compatible with that of the LLM so that the LLM can understand it. And common examples of these are transformer layers or simple feed-forward networks. Lastly, there is a prompt speech mixer that takes the generated audio representation and a prompt that instructs the large language model to create a translation and merges these two things. In this case, the most common approach consists in prepending the speech representation to the prompt. This representation is then fed to a large language model that is responsible to generate the text corresponding to the final translation. Also in this case, several LLMs have been tested in the existing works, and examples of them are Llama 2, Qwen, and Megatron LM. Besides the architectural building blocks, we have explored also the different training settings of the existing works. First of all, we checked what has been trained in each work, and we have seen that they are not homogeneous in this respect. Some of them only train the adapter, others also fine-tune the SFM, and others fine-tune the whole LLM or only part of it with LoRa. In addition, also the training tasks are not homogeneous. In some cases, ASR is the only training task used. In others, ASR is complemented with ST or SQA, and also there have been attempts to include 20 plus tasks in the training phase. Lastly, each solution differentiates from the other also for the supported languages. And there have been attempts to translate from English to many languages or to many languages into English, and also an attempt to build a bidirectional English-Chinese translator. So the question then is, what is missing and what do we need to address with future research on the topic? So first of all, we are lacking a thorough and fair comparison of the current solution to determine which is the best. First of all, we don't know which is the best solution for each architectural component, so for each of the building blocks we have seen before. For instance, we don't know which is the best solution as a length adapter. In addition, we don't know whether the choice of one component depends on the others. For instance, the best length adapter may depend on the kind of SFM we are using. Also, we don't know which is the best training setting. As we have seen, in some cases only the adapter is trained, in others the LLM or the SFM are fine-tuned. So this is another question that we don't know that existing words do not answer. As such, what we need, so on, is an open and standard training data and experimental settings so that we can compare the different proposals and different architectures without the need of rerunning all of them, as this would be extremely expensive. And this would enhance the comparability across works and would enable us to provide insights on all these questions. In addition, we are also missing standard and reliable evaluations. First of all, there is no idea of whether the benchmarks that have been used in previous works are affected by the data contamination issues. Indeed, the LLM and SFM employed are trained on unknown data, so we don't know whether these data have seen some benchmarks or not. Also, the existing works all rely on the blue score, but it has been demonstrated that blue scores do not correlate well with human and unduly penalize LLMs. For this reason, we need to select open multilingual and standard benchmarks so that every work in the area compares on the same thing and we can easily compare across different solutions. And also we need to complement current blue scores with more reliable metrics for LLMs like Comet. In addition, there has been no comparison with the standard ST approaches, so we don't know whether the SFM plus LLM paradigm is actually better than the direct or cascade ST. In addition, we don't know which are the strengths and weaknesses of this emerging approach. And in light of this, we don't know what to work on to alleviate eventual SFM plus LLM weaknesses. For this reason, what we need is a fine-grained comparison with previous approaches and also tailored test suits that can highlight the strengths and weakness of each paradigm. Lastly, one of the main reasons to create this SFM plus LLM paradigm is to be able to leverage the LLM ability in context learning ability to perform more and better to perform more tasks and perform them better with contextual information. However, whether the in-context learning ability transfers to the speech modality and to the speech translation task has not been demonstrated yet. Also, we don't SFM has demonstrated some sort of in-context learning abilities, and there has been no study checking whether the SFM plus LLM solution increases the in-context learning ability of plain SFMs. For this reason, we need dedicated investigation to assess the in-context learning ability of SFM plus LLM. All in all, in this survey, we have created a common high-level abstract architecture of the emerging SFM plus LLM solutions. Through all these building blocks, besides identifying these building blocks, we also provided an overview of the role of each of them. In addition, we have provided many questions that are open for future works and have not been addressed in current ones. So we need to provide a thorough and fair comparison of current solution, assess the in-context learning ability, compare with standard ST approaches, and define standard and reliable evaluations. Thanks for your attention, and see you in Bangkok at our oral and poster sessions.